Okay, I didn't know there was a 15-minute time limit on the videos. Now I know. All right, what I was saying in the last video is that we can use the first law of thermodynamics to look at the heat lost by a peanut, and that should equal the heat gained by the water. And if we did this in class, we end up getting really bad results because we lose too much of the heat to the surrounding air. So we can get better results by putting this whole experiment inside like a tin can, like a coffee can. Then we only lose heat out of the top of the can, so we get a little bit better results. If we actually wanted to get really, really good results, we would use a setup kind of like Joule did that's totally enclosed so that we don't lose heat to the surrounding air. And in real life, we actually do this backwards to figure out how many calories is in a food sample. So let's say that you didn't know how many calories was in a food or in a peanut. So you could put water in the beaker and measure the heat gained by the water, and then you would say, okay, that has to equal the heat lost by the peanut. Now you know how many joules was in the peanut, and then you could turn those joules from the peanut convert those joules into calories, and you would know how many calories was in that particular food sample. So in real life, this is an application of the first law of thermodynamics. All right, but the last statement here is probably the most common in terms of physics. And that says that the internal energy of a substance is affected by changes in both heat and work. So you could write the first law of thermodynamics as an equation. And if you wanted to write it as an equation, the internal energy is affected by changes in heat and changes in work. But it's a little bit more complicated than that because each of those variables is sometimes positive and sometimes negative. So these are called sign conventions. And so hopefully they're kind of common sense. Let's run through them and then we'll look at a quick example. So just know that if the temperature of something goes up, that means the U is going to be positive. And you can kind of get that from U equals 3/2 nRT. If T gets big, U is going to get bigger. And if the temperature goes down, then U will become negative. If you add heat to a system or an object, then that object gained joules. So then heat would be positive. If heat was removed from the system, like you put it in the freezer, then those heat joules are going to become negative because they're going away. If you do work to a system, it becomes positive. Like I could give my joules to a box, and then the box's joules become positive. Work done by a system, like if I'm a system and I do work, I spend my joules, so then my W is getting smaller. So you can peek at this chart if you need help figuring out the sign conventions. All right, let's talk through a quick example and see if it kind of makes sense. All right, a swimmer does this many joules of work. So that says to me that when the swimmer, like when he does work, like he swims from one side of the pool to the other side of the pool, he's losing joules. Okay, that's how he's swimming. He's losing his joules. So that should be a negative. And he gives off this many joules of heat. Why would he be giving off heat? Because he's sweating. He's working out. Determine the swimmer's change in internal energy. So I have to think through. Since he does work, he's losing joules. Therefore, his work number is going to be negative. Since he's working out, he's sweating, he's losing heat. So his heat number is going to be negative. So when I put them all back into the equation, I have negative heat joules, negative work joules. And I can show that my swimmer guy, at the end of his workout, he lost energy. He lost energy due to sweating and to the joules that he had to spend to swim. And at the end of his workout, he is down 890,000 some joules. So that kind of makes sense. And hopefully this example and these sign conventions will help you with a couple of the problems on your homework. Okay, so we're now going to look at the second law of thermodynamics. The second law of thermodynamics can also be said in a variety of different ways. But in general, the second law explains the direction of natural processes. That means it tells us what is going to happen in our universe. There are some natural things that happen. And we're going to go through each of these three in detail in future slides. So I'll talk about them then. All right, the first one is that heat naturally flows from hot to cold. So if you open the door of your house on a cold winter day, your mom may yell at you and say, "Close the door. You're letting all the cold air in." And you can say back, "No, Mom, I'm not. The cold air is not coming in, but the hot air is going out." And so when you stand there in front of the door and you feel cold, it's not because the cold air is coming in on you. It's because all the hot air is rushing past you to go outside. You could also open the door of the refrigerator, and then Mom yells at you, "Close the door. You're letting all the cold air out." And you say, "No, I'm not, Mom." But the hot air from the room is going into the fridge, which obviously is not good. Oh, so we know in nature, in our universe, heat will always flow from hot to cold. Knowing that heat naturally flows from hot to cold, a French scientist named Mr. Carnot had an idea. So I have a picture over here that shows a hot area and a cold area. And so Carnot says, heat is going to naturally go from the hot to the cold. Kind of like a waterfall. Like the waterfall, the water is going to fall from the top of the waterfall to the bottom of the waterfall. And if I could harness that flowing of water, I could build an electrical power plant and produce energy. But Mr. Carnot said he's going to harness that flow of heat to develop an engine. And so if you harness the flow of heat, the kind of engine that you make is called a heat engine. And so a heat engine is a device that harnesses heat to do work, allows you to drive your car, and as a machine it functions due to a temperature difference between two regions. So this is basically the general principle behind the engines that we use to drive our cars. So in this next slide, we're going to go a little bit deeper into a concept of heat engines, and you're going to also see on your homework that this concept is a big part of your homework in terms of the calculations. All right, so heat is going to flow due to a temperature difference. So if we were an engineer, we would have to understand that if I want to make an engine, I got to create a hot spot in the engine or in the car. That hot spot is going to be the gasoline tank. And then I also have to have a cooler spot. And just because it's cooler doesn't mean it's cold. It just means it's cooler than the gasoline tank. And the cooler spot is going to be the exhaust system in our car. So we have this gasoline tank, we have the exhaust system. So heat is going to spontaneously flow from the top to the bottom. And the flow of heat is going to be harnessed. So we're going to build some mechanical device, we'll call it a generic engine, that is going to take that heat that's flowing, naturally flowing, and I'm going to harness it to do work. Okay, when I say do work, I mean to allow me to drive my car. So if I put gasoline in my car and I don't have the cold reservoir, I'm not going to be able to drive my car. I have to have the hot going to the cold. So that's what the whole point of the gasoline is to create the hot region, because then the heat flow is what allows me to drive my car. And then whatever incoming heat is not used to drive my car it is expelled, it goes down here into the exhaust system, and then it is expelled through that system. So I can write this whole thing, this whole, I'll say concept, as an equation. It's not really an equation, it's just like a conservation of energy statement. I'm going to look at all of these things in terms of joules. So I'll say the heat high. I need to create a high heat area. That's the gas tank. I need to know the chemical joules of gasoline. So I need to know how many joules of gasoline I have up here. And then I need to know those joules of gasoline. Some of those joules are going to be used to drive my car. So that's the work joules. And then whatever joules I did not use to drive my car are the joules that I'm going to waste and send out of my exhaust. So I'm not going to make a big deal about this slide right now, but on your homework, you're asked to draw a model of a heat engine. And just like you had to learn how to draw a freeway diagram, when you draw a model of a heat engine, this is what you do. You have to draw a box that is the high spot, another box that's the low spot, and the heat then is going to naturally flow between the high temperature and the low temperature. And then right in here is where I would be building my engine, and then I have an arrow. This is my work that is getting done. And I don't have this equation memorized. I can come up with this equation by just looking at my picture. These joules are going to get divided into some will go to work and the rest will get sent out the exhaust. These joules come in from the gasoline, some of the joules drive my car, the rest of the joules get expelled through the exhaust system. All right, then we look at an engine in terms of its efficiency. Like, is it a good engine? Is it a bad engine? What could I do to increase the efficiency? So we need to pause and make sure we understand the general idea of efficiency. So you could be talking about anything, not just heat engines, but the general idea of efficiency is you take what you put in and you focus on what you get out. So if I put 100 joules in and I only got 80 joules out, then my engine would only be 80% efficient. If I put 100 joules in and I got 25 joules out in terms of being able to drive my car, then we could say the efficiency was 0.25. And so when you divide the out divided by the in, you're going to get a decimal, 0.25. And it's more common to report efficiency as a percent by multiplying it by 100. So that's for any sort of engine. But now let's look at a heat engine specifically. So what do we put into a heat engine? Gasoline. That's the high temperature chamber up here. So gasoline. So we need to know how many joules in that gasoline chamber are we getting. That's going to be the Q high. What do we get out is the ability to drive our car. So that's the W. That's like the plain W in this equation over here. Drive my car. So I'm going to take this conceptual equation that we had and I'm just going to solve for this W here. And that's QH minus QL coming from this. So I'm going to plug that back in right here. And we can calculate the actual efficiency of a heat engine by just subtracting the joules from the top minus the joules from the bottom and divide by the joules from the top, the actual efficiency. All right, it gets a little bit more complex. So Mr. Carnot, however, he came up with a way to determine the theoretical maximum efficiency of an engine, a theoretical. And in short, he said that efficiency is maximized when the incoming heat reservoir is as hot as possible and the outgoing exhaust reservoir is